Assalamualaikum and greetings everyone. We are still on line integrals of a vector field. I want to show you another example. Let's look at question number 2, item D, where here you have vector field F is equal to 2xi plus x zj plus yzk, and we want to evaluate f dot dr over curve C, where curve C is line segment from 221 to point 021 to 003. So here your curve consists of two line segments really. One segment is that connect the point 221 to 021, and another line segment that connect the point 021 to 003. So our curve C here is really a piecewise curve. Okay, now let's look at our notes again on properties for line integral. Here we have the properties for line integral, item 2, where line integrals on a piecewise curve. So if you want to evaluate f dot dr over curve C, where curve C consists of a few piecewise curve, what you do is you evaluate f dot dr on each curve and then add them together. So for question number 2, item D, is where you have a piecewise curve as your curve C. Okay, I need more room. Alright, so this is question number 2D from tutorial 4. We have our vector field F and line segment curve C is line segments from those 3 points 221 to 021 and at 003. So here we have a piecewise curve, which means that we need to evaluate f dot dr over curve C1 plus f dot dr over curve C2. So for curve C1 is a line segment from point line segment from 221 to 021, and curve C2 is a line segment from point 021 to point 003. Okay, all right, so what we need to do now is to evaluate line integral on each curve. Okay, let's start with curve C1. So curve C1 is a line segment that connect the 2 points 221 to 021, and obviously equation of the line is not given. So equation of curve C1 is not given, but it's going to be a straight line. So even though it's not given, we can come up with the equation of the straight line by using the material that we've learned in the previous chapter, vector valued function. Okay, let me refresh your memory on that. If you recall from vector valued function on straight line, so here we have an equation of a straight line in xyz space. The equation of a straight line is equal to RT equals OA plus TD. So OA is the position vector and D is a vector parallel to the line. Okay, so this is the equation that we have to come up with. Alright, now back to our line segment C1. So let's call, so here is a line segment that connect the 2 points, so we need to come up with the equation of the straight line. I'm going to call it vector function R1T. Okay, so first we need the vector OA, the position vector OA. So you can either use point 221 as your point A or 021 as your point A. I suggest you to choose the starting point as your point A. So in this case, I'm going to choose 2, 2, 1 as point A. So vector OA is, vector OA would be 2i plus 2j plus 1k. So you just connect the origin, 0, 0, 0, to point 2, 2, 1. Then we get this vector 2i plus 2j plus 1k. And then remember we have a plus parameter t times a vector d, which is parallel to our straight line. So to get the vector d, which is parallel to the line, let's call this point A and this point B. So vector d will be parallel to vector AB. Okay, so vector AB is a vector on the straight line. So to get vector AB, we're going to use the 2 points. So what you do is you take the destination point minus the starting point. So the x coordinate would be 0 minus 2. The y coordinate would be 2 minus 2. And the z coordinate would be 1 minus 1. So this is equal to negative 2i plus 0j plus 0k. So that would be a vector parallel to our straight line. Okay, let me rewrite that. Okay, so now we can come up with the equation of a straight line. So R1t is equal to 2i plus 2j plus 1k plus parameter t, and our vector d, which is negative 2i plus 0j plus 0k. Alright, and then let's rewrite the, simplify the vector function RT. I'm going to erase this. Alright, so then from there, the x coordinate would be 2 minus 2t. The y coordinate is 2 plus 0t, and the y coordinate would be 1 plus 0t. Or you can write this using parametric equations. X is going to be 2 minus 2t, y is 2, and z is 1. Okay, so what we want is to evaluate f dot dr over curve C. Okay, so f dot dr over curve C1. So we're going to evaluate that one first. So f dot dr, you just use the formula, not this one, sorry, the line integral over vector field, which is in 3D. So we're going to use this. So f dot dr is equal to that. All right, so we have p x y z dx plus q x y dy plus r x y z dz. Okay, back to our problem. So that will be 2x dx, that is p x y z times dx, plus x z dy plus y z dz over curve C1. Okay, since our line integral is 3D, in 3D, we're gonna change all the x, y, and z to parameter t, using parameter t. Okay, so x here will be replaced by 2 minus 2t, y will be replaced by 2, and z will be replaced by 1. And we also need to change dx, dy, dz in terms of dt. Okay, so if x is equal to 2 minus 2t, from there we can get dx. This is equal to negative 2 dt. And if y is 2, then dy is 0. And when z is 1, dz is also 0. 0 dt, which is 0. Okay, now we're going to replace everything in terms of t. So we have 2 times x. So x is 2 minus 2t. And then we have dx, which is equal to negative 2 dt. And then we have xz dy and yz dz. But we know dy and dx are 0. So this is going to be 0, and this is going to be 0 as well. So we have plus 0 plus 0. And then we need the limits for t. So what we do is we get the value of t at the starting point, and also the value of t at the excuse me, at the destination point. Okay, now we have our parametric equation for x, y, and z. So here we have x is 2 minus 2t, y is 2, and z is 1. And here we have our point A, which is the starting point. And this is equal, the x coordinate is 2, the y is 2, and the z coordinate is 1 at point A. And from here you can see that t is equal to 0, because when you replace t with 0 in here, you get x is 2, and here y and z does not depend on t, so it always 2 as for y, and for z it is always 1. So here the lower limits for t is 0. Okay, and then you can get the value of t at point B. Okay, at point B, the coordinates for x is 0, the coordinate for y is 2, and the coordinate for z is 1. And from there you can see that t is equal to 1. Okay, so here you can see that t is equal to 1, because when we replace t with 1, we have 2 minus 2, which is 0. And as you can see, y and z does not depend on t. So the upper limit for t is 1. Okay, now let's simplify this. Okay, so replacing, simplify this, the first term will give you, that will be 2 times 2 times negative 2, which is negative 8. And the second term is going to be positive 8t. We're going to integrate this with respect to t from 0 to 1. So we have negative 8t plus 4t squared. T from 0 to 1, then we get negative 8 plus 4, which is equal to negative 4. So negative 4 is really the value for f dot dr, the line integral along a curve C1. Okay, along curve C1. So we have this is equal to negative 4, and then we just need another value, another work, f dot dr along curve C2. Okay, so now we're going to proceed to the next curve, which is along curve C2. It's a line segment. Okay, line segment from point 0 to 1 to point 0, 0, 3. Again, the equation of the line, the straight line, is not given. So we have to come up with the equation of the straight line. I'm going to call it R2, R2t. Okay. Again, we're going to use the formula from the previous chapter. Let me see. The equation of the straight line from the previous chapter, which is RT is equal to OA plus TD. Okay. All right. So we can use that. So from here, I'm going to use the starting point as our position vector. So this is going to be our point. 0 to 1 would be the initial point. So I'm going to use that point. So the vector OA would be 0i plus 2j plus 1k, and then plus t. And then we need the vector d, which is a vector parallel to the line. Okay, I'm using d again. Okay, now let's say this is point B and this is point C. So our vector d will be parallel to vector BC. Now let's get vector BC from our 2 points, which is on the line segment C2. So what you do is you take the destination point minus the initial point. So in this case we have 0 minus 0, 0 minus 2, and we have 3 minus 1. So from there we get this is 0, negative 2, 2. Okay, so we can replace our vector d here with the vector obtained. So that would be 0i minus 2j 2k. So you take the destination point minus the starting point. Okay, so from, I'm gonna erase this bit because I know some of you can come up with the equation of a straight line quickly. All right, So now once we have the equation of the straight line, as you can see, it is a vector valued function. Let's simplify this. So this is going to be 0i, and here we have 2 minus 2t, and the z component is 1 plus 2t. Okay, so from there we can get parametric equation for x, y, and z. So x is 0, y is 2 minus 2t, and z is 1 plus 2t. So from there we can get dx, dy, and dz in terms of dt. So here in this case, dx is 0, dy is negative 2 dt, and dz is 2 dt. Okay, now let's evaluate the line integral f dot dr over curve C2. Okay, again, this will give us the same same pxyz dx plus qxy z dy plus r pqr xyz dz. So this part here is still the same. So we have 2x dx plus xz dy plus yz dz. But now we're gonna evaluate this along curve C2. And here you can see that x is 0. So this part here is going to be 0 because x is 0. Okay, and here we also have x in it, so this one is also 0. So we only need to evaluate yz dz. Okay, so this is going to be equal to 0 plus 0, and then y here will be replaced by 2 minus 2t, and z will be replaced by 1 plus 2t, and dz will be replaced by 2 dt. Alright, now let's get the value of t at the 2 points B and C. Okay, at point 0, 2, 1. Okay, excuse me. Let me write this again. We have 0, y is 2 minus 2t, z is 1 plus 2t, and at point B, x is 0, the y coordinate is 2, the z coordinate is 1. So from here you can see that the value of t is 0. So the lower limit for t here is 0. And now to get the value of t at point, the destination point is C. I'm gonna save some space here. I'm gonna use the same space. Right now at point C, the x coordinate is 0, the y coordinate is 0, and the z coordinate is 3. So from here you can see that we have 1 plus 2t is 3. Definitely 2t here is 2, t is 1. Okay, and you can check 2 for the y coordinate. We have 2 minus 2 times 1, which is 2. So 2 minus 2 is 0. And you can see that the value of t is 1. So at point C, the value of t is 1. But if you use let's say instead of using point B here, if you use point C, then your t would be different. But my suggestion is always use the starting point as your position vector. Okay, so back to our problem. So this is 1. Okay, now let's simplify this. So the integration is still from 0 to 1. Alright, so here we have that would be 2 times 2, which is a 4. Expand that. So here we have 4t minus 2t, which is 2t, and then times 2, which is 4t. And here we have minus 4t squared times 2, we have minus 8t squared. And integrate that with respect to t. Okay, now integrating 4, we get 4t, and here we have 2t squared minus 8t cubed over 3. Replacing t with upper and lower limits, so here you get 4 plus 2 minus 8 over 3. What is that? 6 minus 8 over 3. Oops. My goodness. Is this correct? Let's see. 2 times 2 is 2 times 2 is 4. And here we have 4t minus 2t, that is 2t times 2 is 4t. Here we have negative 4t squared times 2 is 8. All right, we're good. Yeah, t squared q. All right, so here we have, replacing t with 1, we have 4 plus 2, which is 6, minus 8 over 3 is equal to 10 over 3. Okay, 10 over 3, and then this is on curve C1, C2, and now we're gonna add them together. Okay, so f dot dr along curve C, f dot dr along curve C is equal to f dot dr along curve C1 plus f dot dr along curve C2. And along curve C1 we get negative 4, just this one, C1, and along curve C2 we get 10 over 3. Okay, simplify that. We get 10 over 3 minus 4, then we get negative 2/3. Alright, so this is an example of piecewise curves, because here our curve C consists of 2 line segments. So using the line properties for line integral, we need to evaluate on each curve and then add them together. Thank you.